Hi everyone, welcome back. I'm going to finish off the atomic theory packet. Now, there's very much a connection between the periodic table and the atom itself, okay? And this relationship will kind of reveal itself more as we go through the semester, but really the periodic table is essential for chemists for many, many, many reasons, okay? And the first of those is essentially the numbers in the boxes. Okay, so what I want you to do, and feel free to pause, go grab one. Okay, this is obviously the periodic table, but it's the one I prefer. It's the one from my website. The reason I prefer this periodic table is because it actually tells you the names of the atoms there. Sometimes if I say to you, oh, you know, SB, what's that? That's antimony, right? And you wouldn't know that necessarily right away. But if you look here, you can just read it. Okay, so I prefer this one. Download it, print it. You know, it's a PDF, you can keep it on your tablet or whatever. Okay, so I prefer this. This will be provided with all the quizzes and exams, if needed. All right, so back to it then. So this is where we left it. And notice I do say atoms here. So are atoms electrically charged? Well, the answer is, simple answer is no. Okay, they have charges inside them, right? So protons, which are plus, and electrons, which are minus, but there's always equal numbers, so they kind of add up to zero, if that makes sense. Okay, so an atom is not net, okay? Maybe we can put that there, right? There's no net charge, there's no kind of excess of one or the other, right? So the answer is no. Okay, an ion, which we talked about briefly last packet, or last time we talked, an ion, yeah, an ion has charge, right? And we'll get onto those in a later packet. But there's a process of becoming charged from an atom, which we'll talk about, okay? But atoms themselves, no, they have no net charge. They're neutral, if you like. Okay, so we kind of gave it away. What must be true then in terms of what's inside? Well, for every plus, there's a minus, right? So they equal and opposite, they cancel, yeah? So for every atom, make sure I write atom, right? There is no net charge, i.e. number of protons, which are plus, identically equals number of electrons, which are minus. Okay, so that's the only two things that count when we talk about charge, electrons and protons. Talk about neutrons in a little bit, but electrons and protons, equal and opposite, no net charge. All right. Now, mentioned it here, ions, yeah, that's different. There's a loss or gain of electrons, which we'll talk about, which leads to a net charge. We'll talk about that for ions later. Now, where can you find out the number of protons an atom has? I mentioned it last time. It's actually the small number in an elements box in the periodic table, okay? So, kind of hard to see mine. Take a peek at yours, okay? So, for example, hydrogen, as we mentioned, element number 1 has 1 proton. Helium's element number 2, it has 2 protons. Lithium 3, beryllium 4. And it's the smaller number in the box. Now be careful, because sometimes the placing of the number is switched. In this particular periodic table, number of protons, aka atomic number, is on top. It's the small number, okay? So if I actually, what's the atomic number of silicon? It's 14. Okay, that means it has 14 protons in its nucleus. Ergo, is a word, right? Because all atoms are neutral, 14 protons, also 14 electrons. So it's technically defined as the number of protons, the atomic number, but it's also for atoms the number of electrons, which is helpful. Okay, so where can we find the number of protons? Z, all right, atomic number. So atomic number is code, so Z, right? So Z for hydrogen would be 1, Z for helium would be 2. All right, so pick one, copper. Let's pick a crazy one, copper. There's copper, 29. So copper, Z equals 29. Okay, so you can check that in your periodic table. Not so bad. Note, if I just scroll up just a little bit here, the periodic table is fundamentally arranged, a bit like reading a book, left to right in order of increasing atomic number. So 1, 2, 3 through 10, 11 through 18, and we just read across like reading, reading across the sentences and chapters in a book. we read left to right like reading a book. Okay, so that's how the periodic table is fundamentally arranged in order of increasing atomic number, number of protons in an atom or element's nucleus. That also defines the element. So hydrogen is element number 1. Any nucleus with only 1 proton is hydrogen. All right. Okay. So it's kind of simple. All right. So the number of protons defines the element. That's in a way why the periodic table is arranged in order of increasing atomic number. Okay, because that's an elemental kind of decider, right? If you're a hydrogen, again, 1 proton. If you're helium, 2 protons. Lithium, 3, etc. Okay, so you can kind of relate the two, macro and micro, right? Because I've got a balloon of helium, the atoms inside must have 2 protons, right? So the little red ones. We'll talk about neutrons, which are the other things later. But hey, 2 red ones, 2 protons. Carbon, element number 6, 6 protons. Okay, so all you have to do is look in the periodic table. So we're going to do helium and carbon. So helium, element number 2, 2 protons, right? Carbon, element number 6, 6 protons. And actually it's down here as the first example, right? So carbon, 6 protons, because it's an atom, also 6 electrons. All you need to do, look up silicon, look up lead, which is Pb, in the periodic table, and just write down their atomic number, number of protons, same number, number of electrons. Take you 10 seconds to do that, right? Okay. You're back? Okay, so real quick, silicon, number 14 in the periodic table, 14 protons, 14 electrons. Yeah, it's that easy, right? And then lead, a little bit further down, and lead is heavy, right? We use it for fishing weights because it's got lots of protons in its nucleus. Those are the things that weigh, 82 of them. Okay, 82, and of course, 82 electrons. All right, so fair enough. Now, important thing. Okay, that's not all the information in the box, right? If we look at the periodic table, yeah, pick something interesting. There's carbon, right? So carbon has 6 protons, but there's also this other number down here. And for the early elements, everything up to around 20 or so, it's approximately twice as big, right, as the number of protons. So 6 is the number of protons, and 12, 7, 14, 8, 16, etc., right? Interesting. So what's that other number? Well, it's related to the other thing in the nucleus, which is, yes, the neutron. Okay, it's called the mass number. Now, it's a very important concept, right? This is the mass number. It's the average number of neutrons and protons in a nucleus. As we'll see later, there can be a range of neutrons, so it's never a whole number, right? Not usually, okay? So there's going to be a slight range here, and that's the average of all weights for that particular atom. Those individual atoms with slightly different weights are called isotopes, which we'll get to, okay? So let's write this down. So discussion, the atomic number Z indicates the number of protons. What other type of subatomic particles in the nucleus? Okay, so the nucleus, let's just write this, has protons, and for everything that's not hydrogen, neutrons, okay? Protons are plus, neutrons are of course no charge, okay? So how do the number of these particles get represented? Well, as we mentioned, number of protons equals Z, the small number, atomic number, and then number of protons plus number of neutrons, which is called A, which is the mass number. There's an asterisk, right? Be careful. So that number down there is related to the number of protons and number of neutrons. But because you can't divide a neutron or a proton in half, it always has to be a whole number. Okay, but remember what I said, this is an average. We'll get onto isotopes in a little bit. So that's the periodic table box is not for a single atom, it's for the average of all atoms of that element. Okay, so the asterisk is average for all atoms of an element. Okay, so the top number, the small number, the atomic number is always a round number. You have a fixed number of protons. Number of protons and neutrons, the mass number, so-called because those are the things that weigh anything in an atom, right? The mass number is usually not a round number because it's an average. Some atoms have one or two more neutrons, some have one or two less for an element. We call those isotopes, and the average is displayed, okay? We'll talk about how we represent the mass and number of protons for an individual atom in a moment, but remember, very key thing, and folks not listening right now, and I know you were listening so you'll get it right, folks not listening to this right now will get this wrong on the test because they'll just copy the periodic table instead of what we're going to do next, which is called the complete atomic symbol. Okay, so let's get to that. So the complete atomic symbol tells you the number of protons and the number of neutrons in a single atom of an element, right? Okay, and remember, some atoms maybe have a couple more, some a couple less neutrons. They're called isotopes, all right? So there's you know, I write it down for separate isotopes of an element. Okay, so every atom in nature has its own mass and it has its own number of protons, has its own number of neutrons, and we write that for its own unique, personal, if you like, complete atomic symbol. And there it is, okay, so there's some jargon here, right? So Z we saw was, do you remember? Number of protons, atomic number. A was the mass number. Both these are going to be whole numbers. This is for one atom, right? Okay, and then the chemical symbol, C for carbon, Pb for lead, right? Okay, so if we did carbon, so in this worked example, one atom of carbon, right? The most common form of carbon, it turns out, has 6 of each. And for the early elements in the periodic table, that's kind of how it works, right? So for light elements, same number of neutrons, same number of protons, right? So for carbon, if we look on the old periodic table, carbon is element number 6. 6 protons defines carbon. Carbon has 6 protons. So this is redundant information, which is helpful later, okay? So that must go there. Fair enough. Now it has 6 neutrons. The common mistake would be to put a 6 here, but remember it's neutrons and protons to make the mass number, and that's not a typo. You might say A for atomic number. No, it's Z for atomic number, A for mass number. It's weird, right? And it's 12. We call that one carbon 12, right? Because it's carbon that weighs 12, okay? And that's kind of a shorthand way to do it. And we can abbreviate that down here, right? So down here, because element number 6 is carbon and anything that's carbon has 6 protons, this is information that's redundant. It says the same thing. So we can just skip it, right? So we actually just write C12. So instead of saying carbon, we just say C and then 12 for the mass, okay? So this is an abbreviated complete atomic symbol. All right, now, let's do another one. So carbon 14, which is used in carbon dating, maybe talk about that in a little bit. Okay, carbon 14 is an isotope of carbon, right? So it's carbon, let's just do its complete atomic symbol, that weighs 14, right? So that means it has 2 more neutrons than carbon 12. And that's okay because, you know, it's just like me going out eating 400 donuts, right? Coming back the next day and I weigh more. It's still me. My identity didn't change, but it's, you know, I'm heavier, right? So just because you make an atom heavier, you don't change its identity. So adding a couple more neutrons, maybe taking away 1 or 2, doesn't matter. It's still carbon because it's got 12 protons, okay? So I can have a mass 14 carbon, I can have a mass 12 carbon. It's just subtracting 1 or 2 neutrons, right? Or adding. Okay, so that's an isotope. So an isotope is the same element that weighs a little bit more or less, okay? So that's carbon 14, and you write carbon 14 as an abbreviated. Okay, so try these two. You've got uranium 235, so uranium is here, it's element 92, and chlorine over here. Now chlorine's really interesting. Look at its mass number as an average. So the average chlorine atom in nature, right? If you took an average, of all chlorine atoms in nature, that average would be 35.5, basically, right? So obviously there's no chlorine out there that weighs 35.5. They either weigh 35 or 37, it turns out. There's more 35s than 37s, so the average comes out to in between. Okay, all right. So what you get? So uranium 235. Let's do the whole thing first. So uranium is element number, if we look, 92, right? So 92. and 235. Or we could write uranium 235, right? Okay. Chlorine 35. Well, chlorine is element number 17, and it weighs 35. Okay. All right. There we go. Very good. All right. Now I've got a little bit of a story. I love stories, right? Okay. This is a picture taken from World War II. This is a U-boat, all right? Undersea Boaten number 234. So that's this kind of serial number, if you like, right? Okay. Now, the story goes like this, and this was the story used for the Hunt for Red October, if you ever watched that movie. Kind of a neat movie. Not a true story, Red October, but it was based on this story from World War II. Okay. So you got to remember, it's like 1945. The Nazis are about to kind of lose Berlin to the Russians, who are literally, at the city gates. And what do the Nazis decide to do? Well, they put all their war materials on a submarine, U-234, and this submarine is going to take those war materials to Japan so they can continue the war. So the rocket plane plans and all their fissionable uranium-235. Uranium-235 is the stuff they make nuclear weapons out of, right? So the German stockpile of weapons-grade uranium was sent on its merry way to Japan just before Germany fell. Now, here's where the story gets interesting. The captain of this boat, and it's really interesting because sometimes history changes on the actions of one person. The captain of this boat has a think to himself, and he says, do I surrender to the Americans, or do I go to Japan like a good Nazi? Well, he pops up, and this picture was taken in Boston Harbor. So he surrendered to the Americans, just like the Hunt for Red October, where they basically surrendered their submarine. And, he's taken away, and he lives his life, in America for the rest of his life. The boat carried the uranium-235. Robert Oppenheimer himself convoyed some trucks up from Los Alamos, where the Manhattan Project was going on, and personally supervised the unloading and the loading of the uranium-235, took it back to Los Alamos, and allegedly, you got to read the right books, right? Because history books are always written by the victors, right? The internet isn't written by the victors. So look online for this story, right? The story goes that America at the time did not have enough uranium for a nuclear weapon, right? Did not have enough. And then this falls in their laps. So the uranium-235 was actually delivered to Japan, just in a way they didn't expect. Okay, history. Love history. All right. Now, carbon-14, carbon-12 are examples of isotopes. Okay, so let's talk about that now. So an element, as we mentioned, has a fixed number of protons. All carbon atoms in nature have 6 protons. They may weigh a little bit more individually or a little bit less. Those are called isotopes, okay? And we add or subtract neutrons to change the weight. All right. So it doesn't change the identity of the element. The element is defined by how many protons it has. And its chemistry really is defined by how many electrons it has, which is the same as the number of protons. So it's related, right? Okay. So if we look at chlorine, which is a classic example, mentioned it already, every chlorine atom in nature has 17 protons. But 1/3 of them weigh 37. So they got 20 neutrons, right? And 2/3 weigh 35, so they got 18 neutrons, yeah? So again, this is an average. You can't copy this. You cannot copy this for a complete atomic symbol, okay? The numbers are whole numbers for one atom. This is an average as displayed in the periodic table. Okay, all right. As I mentioned there, don't copy the periodic table. Now, as we looked at earlier in the packet, we count in terms of what's called an atomic mass unit, right? 1 AMU equals the mass of a proton or the mass of a neutron. Okay, mass of a proton is like some crazy number like this, 10 to the minus 24 grams, right? So it's not correct to think about the mass of a proton. Much like we did with the electron when we compared it to other particles, it's a relative scale. So an AMU is the mass of a proton or the mass of a neutron. So therefore, when we weigh something in AMUs, we're just counting how many things are in the nucleus. So carbon weighs 12 AMUs because this carbon-12 has 12 particles in its nucleus, 6 protons, 6 neutrons. Okay. All right. So, bearing all that in mind, you can now put together these isotope tables, right? So it turns out that essentially every atom in nature has isotopes. Yeah, you can literally add 1 or 2 neutrons to everything, and it'll still be that element. It'll just weigh more. Even hydrogen. Hydrogen has 2 heavier isotopes. Okay, extra credit. Okay, if you do this by the due date for this packet, which I think was Friday, 2H isotopes. So regular hydrogen, which weighs 1, just a proton, it's the simplest element, we talked about that. But I can squeeze neutrons in there. What are those other isotopes of hydrogen called? And if you like, you can tell me how many neutrons and protons in each isotope. Obviously 1 proton, right? Okay. So looking at carbon. Okay, looking at carbon. So carbon, it turns out, has 4 isotopes, yeah? Okay, no more, no less, 4 isotopes. All right, let's get my clock out here so I can see where we are. Okay, so the most common form of carbon is carbon with 6 protons, 6 neutrons, and we call that carbon-12, okay? If you look at the mass number for carbon in the periodic table, the average carbon atom in nature weighs 12.011 AMUs. All right, so that means this, on average, just a little bit more than 12 things in its nucleus. So if there's 12 exactly things in the nucleus, that's the most common isotope. 99.9% of all carbons weigh 12, right? Have 6 protons, 6 neutrons. Okay, that's why the average is so close to 12. All right, now imagine we have 5, 7, and 8. Give you a second, right? Just write in these lines here, give me the complete atomic symbol. And also, if you want, you can write the abbreviated atomic symbol. So pause there, come back. All right, you're back. So carbon-12, carbon that weighs 12, all right. Carbon always has 6 protons, 6 electrons. So that's always the same every time. The only thing that changes is the number of neutrons for isotopes, right? Okay. Now this one, carbon, protons, 6, electrons, same number, we don't write it in the complete atomic symbol. This is all about the nucleus, right? But 5 neutrons, careful. What am I going to write here? Neutrons and protons. That's called carbon-11, right? There we go. 7 and 6, carbon-13. Oh, maybe did it myself. 6, 13. And then finally, let's write it. This is going to be carbon-14, 8 and 6, carbon-14. Okay. Now, carbon-14 is very, very important because it's the basis of carbon dating. Okay. Carbon dating, of course, is when 2 isotopes of carbon go to Red Lobster. That's carbon dating. That's a very bad joke. All right. Now, carbon dating, what is it? Maybe you've heard of it, right? So carbon dating stems from the fact that in the upper atmosphere we've got a load of nitrogen-14, right? It's the most stable isotope of nitrogen. So 78% of the atmosphere is nitrogen. And when a cosmic ray, which is basically a neutron, hits, and there's loads of cosmic rays flying around the universe, right? And it's a constant flux, a constant kind of impact of how many cosmic rays per day on the atmosphere, right? We get some nuclear reactions and we eventually make carbon-14. We turn a proton into a neutron. If you take chemistry 102, we do lots of this stuff, right? And so if you think about it, it's actually raining carbon-14 outside right now. Interesting. Now, carbon-14, there actually should not be any carbon-14 around because it's unstable, it falls apart, right? And it has a half-life of about 5,000 years, okay? So half of it's gone after 5,000, another, and then a quarter left after 10,000. So considering how old the Earth is, there should be none, but there is some out there because it's being made all the time. It's raining carbon-14 all the time, right? Okay, now this is important because we as humans, right, are made from molecules that contain carbon. Where do we get carbon from? From our environment. So everything around us, including ourselves, that's organic or native natural materials, contains a tiny fraction of carbon-14, so long as it's alive, right? Okay, because as soon as something dies, it's no longer taking in carbon-14 from the environment, so what's left inside the body actually starts to disappear, and we have what's called a decay curve. All right, if you take nuclear chemistry, this makes sense, and it's an exponential decay. All right, so say I have 100 isotopes of carbon-14. When I get to 50, the time it takes to do that is called the half-life, right? Half left after one half-life, and that's 5,200 years for carbon-14. Then, you know, half of 50 is 25. Another 5,200 years later, I get 25 out of 100 remaining, okay? So all you do, if you want to date something that's really, really old, okay, you just look at the ratio of carbon-12 to carbon-14 in anything that's living or has lived. Okay, it could be a piece of wood from an ancient fireplace, it could be the Turin Shroud, it could be anything, okay, anything that's natural, right? Okay, now that's interesting. So we can date things all the way back to probably 3 or 4 half-lives, so that encompasses all of human history, right? So anything as early as the earliest caveman's fire can be dated pretty accurately, okay? Now the thing is with chemistry, we're scientists, we just report facts, right? So turns out that the Dead Sea Scrolls were actually carbon dated, and they were legitimate from the time period they say they were, okay? So they were real from that time, okay? But the Turin Shroud, which is supposed to be Christ's burial shroud, right, was a 13th century medieval artifact. Interesting. So it's a fake. All right. So the Turin Shroud is, according to carbon dating, a fake. So, you know, if you go to Turin to visit the shroud, don't waste your money. Go down the road and see the soccer game. Okay. Turin. Okay. All right. So back to it then. So there's an isotope table. Every element has its own range of isotopes. Carbon has 4. An interesting one, which is great for academic study, is magnesium. Turns out magnesium only has 3 isotopes, and there they are. Okay, so we have this information. Now this information, and I'll talk about this machine in more detail later, this information comes out of what we call a mass spectrometer. Okay, and a mass spectrometer tells you the mass of an individual atom and what fraction of the sample or what percentage is that type of atom. Okay, and it's very, very accurate. All right, so this is mass spectrometer data. Question is, how do we use this information to find out the average mass of magnesium? All right, now you know the answer to this. Just think about it just for a second. Where would the average mass of a magnesium atom be? You got it, right? Periodic table. So an average magnesium weighs 24.305. All right, so 24.305 AMUs, is that going to be our answer? Question is, how do we turn this information into that average number? Okay, now we can't just add them up and divide by 3 because they're in different abundances, right? So we have to do what's called a mass weighted average. So we have to weight this number more important than these other 2, right? So let me show you how to do that. So how do you do a mass weighted average? Now, before I do that, I'm going to kick off and do the English phrase. I'll kick off and I'll show you that in a second. I'm about to run out of time, so I'm going to briefly stop the video and come back, okay? So, come back in a second. Okay, so we're back. Now, as I mentioned, we're going to take an average, let me just get this right, an abundance weighted or fractional abundance weighted average. Okay, now how do we do that? Okay, so what I've done is I've taken that original data and I want a fraction, not a percent, right? So I turn my percent into a fraction. So 78.99% is actually 0.78, right? And then the contribution it gives to the overall average, it's, you know, it's weighted average percent, if you like, or weighted average mass is this times this. And if you just look at the try it on your calculator. I'll fill them in as we go, okay? And do it to all the decimal places, all right? So, what contribution to the average is this particular isotope? Well, it's this fraction times its mass, and I get for that 18.94578. Magnesium 25, 10%, 0.1, that's easy, right? So we go 2.49858. Here, 11%, 2.86068. Now, those are the contributions to the combined average, if you want, from each individual isotope. Add them up, what you get? 24.30504. And that's pretty much exactly what we thought it would be, right? Because the periodic table said Where are we? 24.305, right? 24.305, we got 24.30504. We got more sig figs. Okay. Check. Easy check, right? Now when you do these, it's an interesting thing because the isotopes are all around the average, right? Okay, a couple AMU higher, a couple AMU lower, but they're around the average number, so they're not going to stray too far from 24 in each case, right? So we had 24, 25, 26, right? Didn't stray too far, all right? So if you ever write one of these complete atomic symbols, you can just look in the periodic table and the mass number in each case will be similar but not identical. Remember the complete atomic symbol, whole numbers, periodic table, and average of all the isotopes. Okay, so it's going to be close each time. So if you get some outrageous number, just double check and it should be close, right? Okay. Now, that mass spectrometer, right? So one of the greatest inventions in science is the mass spectrometer. Okay, it allows you to actually weigh, and I say weigh like this, I'm not putting them on a balance, right? It allows you to weigh individual atoms, or if you like, isotopes, yeah? Okay, so there's a little picture of it. What I want you to do, look at the picture, right? And for a big 5 points of extra credit by Friday, right? The deadline for this work, okay? Tell me how a mass spectrometer works, okay? So you can basically point out, you know, use this picture as a guide, tell me what's happening and how we get this kind of picture of like things that weigh 35, things that weigh 37, and then we have like a ratio of how much of them there is. And there's that kind of 3:2 ratio I talked about, right? So chlorine weighs, on average, 35.45. Why? Because 75% of chlorines weigh 35 and only 25% weigh 37, okay? All right, and that's what comes out. That's what comes out of a mass spectrometer. Should you just put one type of atom through it, you find out, you know, should it have 7 isotopes, there'd be 7 peaks, right? Chlorine only has 2. Magnesium we just did would have 3 peaks. Carbon would have 4, right? Okay, so write me in. Try and keep it brief, right, but get all the facts in there. Scientific writing by its very nature is concise, right? So try and keep it under 200 words if you can. Tell me how a mass spectrometer determines the mass of individual isotopes. Okay. All right. Finally, here's an old one from simple question, let's be honest, right? Okay. So if you understand complete atomic symbols, very straightforward. Write the complete atomic symbol for the isotope that has 29 protons and 34 neutrons. Look on your periodic table. Who is element 29? It's copper, right? So copper. So we'd write Cu29. Now be careful, it has 34 neutrons, right? So 34 is not going there, right? That's the mass number. So 34 and 29, what do we get? 63, okay? Now remember, the mass number is going to be close to the average weight, which is in the periodic table. So 63.546 is the average copper. This one particular isotope weighs 63, makes sense, right? Okay. All right, lots of questions like this in the book. Give it a shot. Stop there. Okay, see you guys next time.